Good day. Today I'll be going over my undergrad research project titled Analyzing the Impact of Cross-Asset Data on Price Prediction, right? So let's get into the meat of it. Assume you have a currency symbol like this, a currency asset like this, and you want to attempt to predict its future prices, right? In order to do that, you'd need its historical data, like all of these data points. You'd use that and try and see patterns and trends, and in order to you have a model that predicts where this might go, right? Not limited to forex, but also stocks such as Netflix could also be subject to the same thing, right? So, say for example, we want to predict where the Euro USD price will go, right? We will take the data for Euro USD, right, and we will train an AI or machine learning model using that data. And that trained model, when you give it new data, it can then give you predictions, right? Now here's the catch. Normally, you usually use the data of Euro USD to get a model that predicts for Euro USD, right? And then my research question generally is, what if rather than just using Euro USD data, we used data from Euro USD, Euro JPY, Meta, Netflix, Amazon, and other financial assets, right? If we used other data sources besides the target symbol itself, would we get better or worse results, right? And I'll cut to the chase for you and just spoil the story right ahead and tell you that the base models here, when you just use the data for the target asset here being like Euro USD and similarly other cases here, and the full is where cases where now you're using data from every symbol that is available in this table here. And the general outcome of my research was that models trained using data from all the symbols, that affect all the symbols, generally performed better than models that just used the target symbol and the target symbol's data set. That is the general outcome of my research. As you can see here, this was I was using a classification model here, and generally the accuracy was way higher for full models as opposed to base models. Similarly for the specificity and the precision, and even my regressionary model, similarly, the full models had way lower root mean squared error compared to the base models, and they also had a higher adjusted R squared. So one might ask themselves, why does it matter, right? Well, the truth of the matter is, in order to train an AI or a machine learning model, it takes resources, it takes time, right? And the more data sets you have, you're putting into the training model, the more time it takes. It literally trains longer. And then also, when you are training a model, typically you go through debugging cycles. This error comes up, that error comes up, so on and so forth. And when you have a big data set like this, the repetitions that occur during debugging cycles, this tends to be a lot harder or a lot more annoying to manage until you get pipelines built for it. But generally this is a lot more to manage. And also just training itself to try and cut down the time. You might try to buy GPUs or subscribe for compute time, but you see now it becomes an additional cost when compared to just this type of data set here, where it's only where you're only using the target assets. So I found that it would be impactful for researchers to know whether there's a significant increase in prediction compared when you're just using the target asset or you're using a data set from multiple symbols, right? Because you'd want there to be a significant improvement when using multiple symbols, so that when you incur the additional costs, those additional costs are made worthwhile because of the, let's say, additional profit you gain by having a stronger model that is trained thanks to this data set, right? So that was the general synopsis of the research project, and I'll go over the code that I used to create the research project, right? So first and foremost, as usual, you import all the necessary data sets. I imported all the necessary data sets, and then from importing, I downloaded my data sets from y.finance. And after downloading the datasets, I created the indicators and the various features, because White Finance would just give you the OHLC columns, which is open, high, low, and close columns, and from those columns you can then calculate the various indicator columns, such as your simple moving averages, your exponential moving averages, your Bollinger Bands, and all those popular indicators for financial assets. So from that I would calculate them using the Taleb library, and then I would also use the Taleb library to create indicator columns for what patterns were present at that particular time for each row in the data sets. And lastly, here's a bit of cleaning of the data set and the formats in which it came from White Finance. And ultimately I created a combined data frame where the rows were observations in time and the columns were the features of the various assets, all combined into one gigantic data frame. I think it was something like 1,000 rows and around 800 features, which is already fishy. Like, it's typically you want the number of features to be around 10% or less of the number of rows you have, but there are ways I mitigated for that, to be shown down below. So at this point, this is like importing the parquets. I had stored the data files in parquets because the data was becoming explosively big, and parquet is a really good way to help solve that. It's easier to read. And the classical checking for missing values, you find that there were no missing values, and then a bit of descriptive data analysis here. And from this descriptions we got the count, how many rows there were, the means, the variances, and the general take home from doing the descriptive analysis was, one, the variance of the forex pairs was way less than that of the variance of the equities, which is explainable by the fact that variance can be a measure of risk, in that forex pairs tend to move a lot less radically, and hence are exposed to less risk compared to equities. And also similarly, where there's less risk, there's less reward, right? And then another thing we noticed was that generally there was negative kurtosis for most of the symbols, except a few outliers. But the negative kurtosis was basically telling us that rarely do prices deviate very strongly from the mean. But yeah, that was pretty much the case. Did a bit of visualizations here. Yeah, you can see most of them are here, most of them are below this line here, indicating the negative kurtosis I was discussing. And moving further along, yeah, this is the correlation part. This is where I did a bit of a correlation diagrams, just to try and see if yeah, you can see the correlations between the symbols as well as the equities, since I'm going to be using them each other for them to predict for each other. But yeah, after my correlational studies, you can observe that generally there's a lot of correlation, but then I didn't try to interpret too much from it because of the high prevalence of the Euro USD, which is like the backbone of the global economy, and whatever moves for the Euro USD, generally you feel shocks and pains for it across the globe. So I could try and interpret these for you, but the general move is that you generally see USD pairs moving in similar fashion. Alright, and before moving on to inferential stuff, a bit of pre-processing I did. I split my data into both continuous and categorical columns, which is something I love to do if you've been following my portfolio videos for now. And then I used that so that I could scale my continuous columns. I would hope not to scale my categorical ones, of course. And then after that we moved on to regressions, right? And for my regressions I used elastic neck regression, which is L1 and L2 regularization combined. Why would I do that? It's because my data set had a lot of collinear columns, right? And they being collinear columns, it violates it violates the assumption of simple linear regression, or OLS regression, ordinary least squares regression, that the columns or the features should not be multicollinear. But since the features are from OLS, like are from OHLC, I wanted to say, from OHLC columns, you tend to find a lot of collinear columns. So I resort to using regularization, right? And I balanced L1 and L2 regularization because, as I mentioned earlier, I had found that my dataset had like 800-ish features alongside 1,000 rows of dataset. Clearly, dimensionality reduction had to be done, and that's why I used L1 and L2 together, because the other perk of regularization is that it does dimensionality reduction for you, either by shrinkage or by true elimination, by setting the coefficient to 0 for whatever particular feature that may be. I did not use PCA in this instance, but yeah, these are the regressions I made. So what I would do in order to create my target columns basically would be that for a particular row, which represents a particular hour or a particular day, actually, we look at the opening, we look at the close, right? And you subtract the opening from the close, and you get the movement of that particular day, be it positive or negative, right? So the numerical value, that's the one that was targeted by the linear regression, and then whether or not that number is positive or negative, we then used, if the number is negative, I believe I set it to 0, and if the number is positive, we set it to 1, and that was the logistic, you turn it into a binary outcome, and then you use the logistic regression in order to predict towards that outcome. Basically, that's how I did my target columns. And so, yeah, pretty much it. I had balanced L1 and L2 regularization. The only thing I was grid searching for was pretty much the alpha, which is the strength of the regularization. I was grid searching for that. And yeah, as I was doing the regression, and this looks a bit convoluted because I was saving the metrics, right? So like you'd find that for each model, for each symbol has to have its own base regression done, its own full regression done, and then from there you'd have to save all of these metrics for each model or for each symbol basically. So that's why it looks a bit more convoluted. I could have opted to parallelize the process so that each symbol is the linear regression and or the logistic regression is done in parallel, but with time and tuning and scaling, having scaled the data set, even just doing it linearly just turned to an affair of between 2 to 4 hours of processing. So I just decided not to overcomplicate the matters with parallelization, because debugging parallelized operations can be a bit on the hard side for me, a person I regard myself as a junior data science developer. But yeah, that was pretty much the case. This whole convolution is primarily caused by the recording of the results, because it was important. And also for each model I actually recorded the coefficients of each feature, because they helped in a later section, a later correlation I wanted to do. So the linear regression and the logistic regressions for each symbol were done, and then after that we do a sign test of the results, right? So let's look at it this way. Yes, so you're looking at the base and then you're looking at the full. You'd want to know statistically, is there a significant difference between these two, right? And the sign test is what I opted to use for this. People typically use things such as paired or t-tests, and in some industries it's known as a A/B test. But I wanted to see if there was a significant difference between the base and the full outcomes for both RSME and adjusted R squared. Because if I know if there's a significant difference, then clearly to be shown that this being larger, generally larger than this, it is significantly larger. And it makes sense then to attempt to be fully commit to training your models in the fullness. Like fully train your models using the full data set instead of just the target assets data set, right? So I used the sign test to see if there's a significant difference between the base and the full, and the sign tests pretty much came as obvious. They showed us that in this case for accuracy we rejected H0, which means there was a significant difference. And also interesting, for both RSME and adjusted R squared, still there was also a very significant difference, which showed that truly and clearly it was better, it was significantly better to have a full model, right? So going back to our diagram, it's better to train it using this way, right? And as I had alluded to earlier, it will generally be more expensive, but the significance when you scale your model and its outcomes, it could generally, the significant difference could pay for the additional costs that come with using this as compared to using that, right? So that was pretty much it. Like, I could go on to, I did a spearman's rank test, right? So this was let me explain it to you, right? So assume that now you know that we have discussed, we know that it's better to use this, it's better to use all of the symbols, right? And then you might ask yourself, maybe you want to cut down on the symbols, right, in order to try and manage costs. So then the question I ask myself is, since we're predicting for EuroUSD, and maybe we know that Meta and Netflix, right, I'm giving a hypothetical, Meta and Netflix are correlated with EuroUSD as compared to EuroJPY and Amazon, right? Let's just say that for a hypothetical case. Then the question I would ask myself is it better that I just include Meta and Netflix? Yeah, is it better that I just include data from Meta and Netflix and I can exclude the ones from where there was a poor correlation? That was generally the purpose of the correlation test I asked myself. It was a means to see if it was better to use data from correlated symbols. And the general outcome was that the correlation had no bearing, basically. Like sometimes you could find that the strongest features came from symbols or from assets that were not so strongly correlated with the target asset, but it still provided, it was still a great feature and provided a lot of information to the model. And so, yeah, that is basically the summary and synopsis and overview of my research project. The research project itself, like the paper itself, is also in my GitHub, as well as the code that I had gone through, the code that was ran in order to create this project. It will also be found on my portfolio repository on GitHub, and the link to my repository is in the description of this video. Once again, I thank you for watching my portfolio videos. Wishing you all the best. Goodbye.